All right, guys, here we are with the second question in this set of FRQ problems. This one is our experimental design problem. Now, the experimental design problem is probably going to take you the longest out of the 5 FRQ problems, just because it's the one that's most likely to require the most amount of thought, and also the one that's most likely to require you to, at the end of your response, erase everything and retry something else because you don't think it quite works. So we want to be very careful with reading through the entire problem so we understand everything that it's asking for before we start answering. Or else you will be that person at the end who's like, oh snap, this is not quite the experiment that I need. Let me start over. So to start off, let's go ahead and read the whole problem together. A disc-shaped platform has a known rotational inertia. That's fantastic. So we know I. The platform is mounted on a fixed axle and rotates in a horizontal plane as shown above. A student wishes to determine the frictional torque exerted on the platform by the axle as the platform rotates. The student has access to equipment that would usually be found in a school physics laboratory. Part A says, describe an experimental procedure. Okay, you'll know it's the experimental design problem because it'll always tell you to describe or to create an experiment in some way or another. The student could use to collect the data needed to find the frictional torque exerted on the platform while it rotates. AI says what quantities would be measured. AII says what equipment would be used for the measurements and how would that equipment be used. AIII says describe the overall procedure to be used, including any steps necessary to reduce experimental uncertainty. Give enough detail so that another student could replicate the experiment. B says describe how the data from the measurement could be analyzed to determine the frictional torque exerted on the rotating platform. And then moving on to the next page, we have a part C. The premise to part C is that it is often assumed that the frictional force between two surfaces is independent of their relative speed. However, the details of the axle's construction are unknown, and it is possible that the frictional torque of the axle depends on the platform's angular speed. This is saying that it's possible that due to the material that the axle is made of, the faster that the disc is going, this could affect the coefficient of kinetic friction between the disc and the axle. Are we actually measuring this in our experiment above, or are we not? Are we assuming constant acceleration? Yes or no? Now, either answer, yes or no, could be correct depending on whether or not it's true for your experimental design. If you answered yes, describe which part of your analysis depends on this assumption. If you answered no, explain how your analysis does not depend on this assumption. All right, and then finally, for D, briefly describe how the experimental procedure described in parts A and B could be modified to determine whether the frictional torque stays constant as the angular speed changes. If no modification is necessary, state that explicitly for this point. In either case, describe how the data could be analyzed to determine whether the frictional torque stays constant as the angular speed changes. So I'm noticing a couple of things here. I'm noticing that if I can design an experiment that doesn't assume constant angular velocity, that doesn't assume constant angular acceleration due to the friction, then my part D here could just be like no change is necessary for the point. All right, that's an ideal situation. But now let's come back up to the top. All right, let's start to analyze what's going on here and what we can use. All right, so we know that we're looking for torque, and we know that we already have I. So to get started designing an experiment, I'm going to look through the formula sheet to see if there's anything that has both torque and I, because that's probably going to be the relationship that's going to allow me to set up the simplest experimental design. All right, so I do know from the formula sheet, according to Newton's second law, that torque, let me get my pen, torque is equal to I times angular acceleration. All right, so I'm looking for torque, and I already know I, so that makes me feel like finding angular acceleration through my data is the way to go. All right, so then that said, how would I measure two things to get angular acceleration? Well, based off of the definition for angular acceleration, we know that that's going to be the change in angular velocity over change in time. All right, cool. That means that if I can put together a plot that's going to put angular velocity versus time, then my slope of that plot should be angular acceleration. I can take that slope, multiply it by I, which is known, and I'll have torque. All right, so then let's go ahead and figure out what quantities we need to measure in order to get angular acceleration. Based off of what we have here, it looks like we just need velocity, angular velocity, and time. So with a disk, how can we measure angular velocity and time? First off, the quantities that we want to measure are angular velocity, okay, and we want to measure time. Go ahead and write these out as you're putting yours. Angular velocity. We want to measure angular velocity and we want to measure time. How are we going to do that? Well, for a disk, the easiest way to measure velocity, for a disk that's spinning, the easiest way to measure velocity is to find its period, because you can easily mark a disk and see how long it's taking to spin one revolution. All right, so what would be a good way to do that with equipment found in typically found in a high school physics laboratory? Well, we could use a photo gate. A photo gate works really well with a spinning disk because you can orient it in any way you want. So you can kind of set it up at the edge of the disk so that maybe like a little tape marker could just like trigger the photo gate every time it passes one revolution. And then you just set up your photo gate to some data logger software, and then you can see the time in between each full rotation. So that's what we're going to use today, a photo gate. And let's see, what else do we need other than a photo gate? Not sure. I think that's pretty much all we're going to need here, because all we need is time and angular velocity. We're going to be able to get that through the photo gate. So how are we going to use it? We're going to go ahead and set it up. Set up to measure the period of the spinning disk. All right, it might be useful to say that we're measuring angular velocity through period here, just to make it very clear that we understand what we're measuring. And then for describing the overall procedure to be used, including any steps necessary to reduce experimental uncertainty, we're going to go ahead and say that we are going to orient a photo gate such that its light beam is perpendicular to the tangential direction of the disk, so a light piece of tape placed, let's rewrite that, placed at the edge of the disk will trigger it at each pass. Okay. So that should be enough detail so that somebody else could kind of set up and orient their photo gate in such a way that we're going to trigger it with some light tape or some other similar marker every time that point on the disk passes through the photo gate. All right, just in case you're not 100% sure how a photo gate works, it's kind of like this this U shape, okay? And on one end, and let me like kind of draw it two-dimensional here. On one end, it's shooting a light beam to the other end. And this light beam is expected to be continuous, but if something passes through it, it marks that that time point from the time that you start measuring, and kind of sends it to some software data logger so that it'll tell you at every time point that its light beam was interrupted. This can clearly help us measure the period, because if we have some kind of light tape that doesn't affect our rotational inertia passing through this light beam every time it passes one revolution, then we have the period. We have timestamps for the period. That said, describe how the data from the measurement could be analyzed to determine the frictional torque exerted on the rotating platform. Yeah, that's great. So the idea is that we were going to plot angular velocity with time, but what we have is period with respect to time right now. But that's okay because we chose to measure period because period is very easily relatable to angular velocity. We have on our formula sheet that t, which is period, is equal to 2 pi over omega. Okay, so that means that omega is just equal to 2 pi over t, over period. So now that we have our period, we just divide 2 pi by our period, and now we have data points for our angular velocity. So what we're going to do is we're going to go ahead and plot angular velocity and make sure that you actually put your units here, radians per second, with respect to time. And we're going to get these time markers from each photo gate marker. So for whatever period we're getting a angular velocity data point from, we're going to use that marker from the photo gate as our time marker. And then we're going to go ahead and start plotting. And what we should start to see is that initially, our initial data points for angular velocity are going to be somewhat higher. And then over time, our angular velocity is going to drop because we know that there's going to be some frictional torque from the axle onto the disc. And so if that torque is constant, regardless of the speed, then what we're going to see is a linear relationship here. And we can just go ahead and take the slope of that linear relationship to be equal to angular acceleration. And from there, we're home free, because if you take angular acceleration and multiply it by moment of inertia, which is known, then we finally have our frictional torque. But the thing is that this is kind of a special setup, because this graph doesn't necessarily have to be linear for it to be useful. Because if at these higher speeds, there's more torque, then what we're going to see is a steeper slope. We're going to see a steeper slope. Let me do this in red, actually. We're going to see a steeper slope initially that's going to kind of level out a little bit more as we go down. So this red line would indicate that the torque, or the friction between the axle and the disc, is actually dependent on how fast it's going. All right, but it's still very useful because we can take the slope to any tangent to this curve as the angular acceleration at that point. All right, so we can still find the frictional torque at each point. So I really like this design, and this allows us, based off of that same argument, this allows us to say that no, our experiment does not depend on the assumption that frictional torque is independent of the platform's angular speed. Okay, so we're not assuming that it's going to be constant regardless of speed. The reason for that is what I just explained up here, because our data is going to show a linear relationship if it is independent, and it's going to show a curve if it is dependent. And either way, this is a useful curve to us. All right, so we're going to go ahead and explain something along those lines here, that our data will show a linear relationship if it is independent, or a curve if it's dependent. And then that allows us to answer D in the very easy way of no modification necessary. All right. Now, based off of what we've discussed here, all right, as long as you continue answering that we can take acceleration, multiply it by by rotational inertia to find torque, then we have 11 out of 12 points based off of everything that I've just said here. The way that we are going to earn our point for minimizing experimental uncertainty is, well, there's lots of ways, really. You just have to consider your procedure and just make a statement about how you're going to ensure that there is no room for error. For example, we're mounting our photo gate in an interesting orientation. You can make a statement suggesting that you are going to ensure rigid and stable mounting of your photo gate so as to not corrupt any of the data. Also, you could make a statement about your markers suggesting that you're going to make sure that it might be rigid in some way, and that it will allow for the marker to actually trigger the photo gate every single time it passes. A simple statement suggesting that you're going to take extra caution in setting up your procedure is usually all that's needed in order to get the point for minimizing experimental uncertainty. So there's lots of different ways you can grab that point. All right. So don't sweat it too much. Just think about whatever procedure that you've come up with and just make a statement that you're going to make sure that it's set up properly, so to speak. That said, good luck. If you have any questions about how we've answered this question, or if you want to discuss a different a different answer that you think might work and you want to talk to me about it, feel free to do so, because this is going to be the answer, the FRQ question that's going to have the most possible correct answers. All right. Remember, we want it to be as simple as possible though. So my setup was as simple as I can make it because I knew we only really needed one piece of equipment other than the actual disc and axle itself. That said, good luck studying. I'll catch you on the next one.